The discussion so far has been on wetting on smooth surfaces. These are ideal smooth surfaces without any roughness on the surface. But realistic surfaces are not exactly smooth. You'll have a lot of undulations in the surface. If the surface is manufactured artificially, let's say using some machining operation, then the machining process will introduce a roughness. One such example is shown on your screen. There's a droplet that you see sitting on a rough surface, and there are lots of undulations on the surface. The size of these undulations depends on the how good is your manufacturing process. But such surfaces also occur in many natural applications. The most common thing that comes to mind when we talk about wetting and capillarity is the so-called lotus effect. Now, in a lotus leaf, as all of you may know, you'll find these lotus leaves typically in muddy water, dirty water, but still the surface of the lotus leaf tends to be very clean. That's because if any tiny water droplet is formed on the surface of the leaf, then it quickly rolls off and the leaf remains dry. And in the process, when it rolls off, it also takes away all the dirt and the dust that is sitting on the leaf. So you may have heard of words like lotus effect, rose petal effect, um, uh, self-cleaning surfaces, biomimicry. Now, if you want to understand some of these words, we need to look at wetting on rough surfaces. And when it comes to engineering and technological applications, we can also manufacture controlled rough surfaces or textured surfaces. Now, um, in I already gave one example of natural rough surfaces, that is in the lotus leaf. In the lotus leaf, what you have is a series of tiny pillars, anywhere between 20 to 50 microns, and they're about 10 to 20 microns in height. These tiny pillars, and on top of these tiny pillars, you also have a typical wax coating that is there. You have these wax crystals that are sticking out on top of these pillars. But wetting and wettability is a very important aspect when it comes to water birds. There are several birds which basically inhabit water bodies. Some of them actually even dive into water to hunt. Birds like egrets, kingfishers are an example. You also have ducks which swim in water, and if you notice these feathers of these birds, again one has to understand what is the wettability on rough surfaces, because these birds have this remarkable property that the water doesn't stick to these feathers. And increasingly, it has with people using active wear as in clothes which basically moisture wicking clothes, which are clothes which dry out very quickly. Again, it's very important to understand how water basically stays on the surface and rolls off on the surface. It's also another very important application where wettability plays an important role is basically making a sort of coating on windshields. On a car windshield, when you're driving, you don't really want water droplets to be staying on top of the windshield because that impairs visibility. So it is very beneficial to have some kind of a coating or some kind of surface where the water droplets don't stay on the surface. Now, roughness, it's not necessary that roughness is undesirable. I've given you several examples where roughness is desirable, such as in the lotus leaf or in the water birds. It is desirable. So, one needs to understand what's the connection between roughness and contact angle. Now, why do I talk about contact angle? Now, if you take a smooth solid surface and you have a droplet that's sitting on the solid surface, then we've already shown that the Young's law is valid very close to the contact line. And the Young's law essentially relates the three surface energies that are present in the problem. Now, of course, this is under the assumption that the contact line is free to move on the surface and it's not pinned. Now, if you see the figure that I'm showing you in the two figures that I'm showing you on the screen, in the first case, I've basically said if you have a rough surface, is the angle really the Young's angle? That's a question mark that we want to understand. The other example that I also is relevant in this context is a droplet that is sitting on a tilted plate, or in a, let's say it could be an example of a car, a water droplet on a windshield of a car. Now again, notice that the angles on the front and the back of the droplet are different. This at least suggests that you can have more than the Young's angle, something different from the Young's angle. So, and when you basically do make measurements of contact angles on rough surfaces, you see an angle which is different from the thermodynamically observed Young's angle, even though the surfaces still have the same surface energies. So, in other words, the roughness and the way the droplet basically interacts with this rough surface changes the so-called apparent contact angle. We want to look at what's this relationship, and there are several important studies that have been made, and I let me also point out that this lecture that I'm going to give is only a preliminary primer on this topic. This is still an active area of research, even though some of the early theories were given in the 1930s and in the 40s, but still an active area of research, primarily because we are now able to we are able to engineer surfaces precisely the way we want, so that we can test some of these theories, and several new discoveries are being made. For example, the petal effect, or the rose petal effect, is one such recent discovery that was made. Now, there are pioneers in this field such as Casey and Baxter. We will look at one such model by them. And they published a paper, I think, back in 1948. And I'll read out a sentence from their paper in 1948. It says, at present, I'm quoting from their paper. It says, at present, it is sufficient to note that water rolls off a duck's back because of the structure of its feathers, rather than because of any exceptional proofing agent, and that man's attempts to make clothing with the water repellency of a duck should be directed to perfecting an appropriate cloth structure, and I highlight the word structure, rather than as present to searching for an improved water repellency agent, a water repellent agent. Now, what Cassie and Baxter realized back then itself is that sometimes it may be worthwhile to actually focus on the structure of how fabric is made. In this particular case, they were primarily looking at fabric. In fact, their work was probably, I think, funded by by wool industry. So they suggest that structure is important, not just the chemical nature. Note that the chemical nature, or chemistry, determines the surface energies, but we can also basically play around with the contact angle by basically playing around with the structure. And structure in this case changes the roughness. Now, Cassie and Baxter's original work was in the context of wetting on fibers, primarily cylinders, and they were looking at wetting on porous surfaces. Unlike another pioneer in this field by the name of Wenzel, who looked at a different kind of wetting mechanism. So we'll look at some of these things. So, but before we get into wetting on rough and textured surfaces, let's quickly recap what we have seen for wetting on smooth surfaces. So I do this by using using the system that we've already studied, a droplet sitting on a smooth surface. And the figure that you see here is a snippet of what we've already derived earlier. So we'll start with wetting on an ideal surface, ideal smooth surface. Let me qualify what I mean by ideal. So ideal as in, this is a surface which is smooth. Again, smooth, let me quantify what I mean by smooth. Smooth is atomically flat. This is a surface which is chemically homogeneous. And it's isotropic. The properties on the surface are uniform in all directions. It's non-reactive and insoluble. It's non-reactive and rigid. Does not deform. Okay, on the surface. Now, if we have such a surface, we can write down the energy, the free energy for such a surface. Let's write down the free energy for such a surface first. So if we write down the free energy in terms of, let's say, this is a functional. This is a function of h and hx, and also the position x, where you're going from 0 to a, 2 pi gamma 1 plus hx square and times x. Let me explain what we are doing here. So unlike the previous analysis, there is another reason why I'm repeating this analysis, because all the previous analysis were two-dimensional. I want to extend this to an axis-symmetric case. So in an axis-symmetric case, what we are doing is we are considering a small control, a small region here, which is at a distance of x and of thickness dx, and the height of this element is h of x. If I have such a region, then we are writing down the energy for this region, and we are integrating from 0 to a rather than from minus a to a, because this is an axis symmetric system. So you go from 0 to, the angle goes from 0 to 2 pi. That's why you have the factor 2 pi there in front. So we have this. And finally, instead of putting a gravitational force, let me just put an arbitrary additional energy. I'll explain what this is. This u of x here that we are seeing here, it's because of an interaction of an arbitrary field. This is an additional external field. This units is joule per meter, and this quantity u of x, which could be a function of height as well, this would be something like 0 to h of x, 2 pi x w of x comma y dy, where w of x comma y is called the volumetric energy density. So for example, for gravity, we would simply have w of x comma y to be rho g y by 2, and therefore I simply would have u of x comma h of x would simply be half x by rho g h square. Okay, where rho is the density of the liquid. Notice the parallel to what we had taken for the energy, the potential energy contribution and the energy functional for the 2D case. This is exactly the same thing, but for an axisymmetric case. The reason I wrote this in the form of u of x comma h rather than just gravity is because I also want to emphasize that this variational approach that we are trying to employ in some of these problems is a very, very powerful technique, and it can be easily extended to other kinds of external fields. It not necessarily a drop in a gravitational field. The drop could be in other kinds of fields, and the variational approach naturally carries forward to such a situation. So now let's basically do the analysis for this. So what we had done is, if you look at the analysis that we had done in the previous couple of lectures, we basically wrote down the energy functional. We looked at the variation of this energy functional, which I called it as delta of J. And then we basically we set each term in this bracket, in this variation, to 0. And when we did this, we got these boundary terms, which I'm highlighting for your benefit. You look at this boundary terms, this one, and the other boundary term. These are boundary terms. And these essentially give us the contact angle condition at the contact line. In fact, they give for a smooth solid surface, they give us the Young's angle. And the last relation gives us the Euler-Lagrange equation, and this Euler-Lagrange equation gives us the Young-Laplace equation. And the Young-Laplace equation, in other words, is an equation which allows us to calculate the shape of a droplet, provided we have the necessary boundary conditions. Now, if we just take this energy functional, we have not imposed a volume constraint. Now, if the droplet does not evaporate, in other words, if we impose a volume constraint where the volume constraint V would simply be 0 to A 2 pi x h of x dx, and if we say that this volume is constant, recall that the way we do this is basically use the method of Lagrange multipliers. Then the functional J, which is a function of x, h, and hx, where hx is the derivative of h with respect to x, the functional essentially becomes 0 to a f of h, hx, and x dx, where this quantity f essentially becomes 2 pi gamma x into 1 plus hx square plus 2 pi x, the difference in the surface energies of the solid, liquid, and the solid, plus this external field that we have here, this could be gravity, plus the constraint from the volume, that is lambda times 2 pi x times h. Note that we still have to do an integration from 0 to a to get the total energy function. So the idea is we want to do a minimization on this. Minimization problem of this functional. That's the idea, right? Now lambda, as you may recall, is the Lagrange multiplier, and if we use either of these constraints, meaning the boundary terms that I have highlighted in yellow, then how does the boundary term look like? The boundary term essentially becomes is f minus del f by del hx of hx at x equal to a is 0. That's the boundary term. Notice that this is identical to what I had written earlier. F minus del f by del hx at a or b. There we had a and b because it was a two-dimensional problem, but here we have an axis-symmetric problem, so it goes only at a. And applying at a is basically applying it all along the contact line, which is a circle when viewed from the top view. Now, when we apply this boundary condition, then if we substitute the expression for f, substituting f, we get gamma times 1 plus hx square plus gamma SL minus gamma S plus, this is minus gamma hx square by 1 plus hx square. This quantity has to be evaluated at x equal to a. We set it to 0. And if we do some quick simplification, what we got was 1 plus hx square plus gamma SL minus gamma S hx square minus gamma hx square is 0. This and this cancels out. And finally what we have is gamma plus gamma SL gamma S of 1 plus hx square is 0. And if you recall the region very close to the contact line, if this is the contact line and if the angle, let's say, is theta y, and you look at a small element very close to the contact line, if you draw a triangle, let's say this is dh and this is dx, then we find that tan of theta y is dh by dx. Technically speaking, it should be negative because I have this is minus dx and therefore minus, but since I'm having square of it anyway, it does not matter, and therefore I have this quantity, square root of this essentially becomes secant of theta y. Okay, and I have cos of theta y is gamma s minus gamma sl by gamma. Now if you notice here, I'm using a different symbol for the equilibrium Young's angle. I've used the subscript y rather than e, but they're all essentially the same. It could be equilibrium angle or the Young's angle, and that's also evident in this figure. Different angles that I want to illustrate. I want to find out whether this angle is the angle on a rough surface, apparent contact angle on a rough surface. Is it really different from that of the Young's angle? And therefore, to highlight that, I've used the subscript y. Now that we've actually done this analysis, there's also one more thing that we see, and I should emphasize this. This is an analysis that we've done for a axis-symmetric geometry. The previous analysis was done for a 2D geometry, and yet the Young's angle emerges even for an axis-symmetric geometry. This is not at all surprising because ultimately whether we do it with gravity, whether we do it in 2D or axis symmetry, what ultimately matters is that we are in a region very, very close to the contact line, and when we are so close to the contact line, the only thing that matters is the dominant physics at the contact line, which is the different surface energies. Now there is another way to also arrive at this result, and I'll also illustrate this very simple way of doing this, which is, if you consider, let's take a flat surface, okay, and you have an interface like this, and we are making an angle. The local angle here is, let's say, is theta y. So let me basically the local angle is theta y, right? Now we have three surface energies. Let's call this as gamma. Then we have, this is gamma s, and finally we have gamma SL, solid liquid. Now what we will do is, we will take the surface and ask what would happen if the interface moves by a certain amount. So the interface originally was here, and I have to make sure that the angle remains the same. The interface originally was here, but now it has actually come to the new position here. My drawing skills are being tested here. That's the new position. So the angle has not changed, but the interface has moved by a distance of dx. And in the process, it has essentially, we have created an extra surface here, which is dx times cosine of theta y, right? This is theta y. The angle remains the same. Okay. Now, what we want to do is, we want to find out what is the work done moving the contact line by distance dx. Contact line by a distance dx. Now, if you want to write down this work done, we say this is simply dw is gamma solid minus gamma solid liquid times dx minus gamma cosine theta e d theta x. So this first quantity that you see here, this is basically because of contact line motion, because the surface, it has actually spread on the solid, right? It has spread on the solid, and then the second part that you see here is it is from creating a new surface. Now, the sign of this dw is not very important. That in other words, I could be moving left or right, ultimately we want to find out if there is a small change in the position of the contact line and the interface moves on the surface, what is the work that needs to be done to move it, and provided the angle remains the same, right? So the sign does not matter because in equilibrium dw is 0, and if I do this, I get gamma s minus gamma sl essentially becomes gamma cos theta e, and therefore we get Young's law. Okay. Now, this particular simple way of our analysis is it's definitely much simpler than, it looks definitely much simpler than the variational approach that we have taken, because it tells us that I can just move the contact line a bit and the interface a bit, and then ask what is the change in the work, what is the change in the energy or the work done, and hence find out the set that work done to 0 in mechanical equilibrium and get the Young's angle, right? So I think it's time to call it an end to this lecture, but let me illustrate what's going to come in the next lecture. So we now have looked at just a smooth surface. Now we want to look at wetting on textured surfaces. There are 3 kinds of textured surfaces that we'll be looking at. The first one is where you have a droplet that is sitting on a rough surface, and this is an idealized rough surface where you have a sawtooth pattern, but we'll see in the analysis that this idealization is not necessary. It could be an arbitrary rough surface, and the droplet, basically the liquid of the droplet, penetrates all the way into those little grooves that you see. You can have, when I say rough surface, the common thing that one may be accustomed to thinking about is a physical roughness. But if you're talking about only wetting, where surface energies are important, you can also have a situation where it's not really, it could be still a smooth surface, but it's not really a chemically homogeneous surface. Chemically homogeneous surface could be, an idealized chemically homogeneous surface could be illustrated as seen in the second figure, you have a droplet that is sitting on a checkerboard pattern where each square has a slightly different color. If you notice, they have different grayscales, and each of these squares actually has a different surface energy, and therefore the droplet is actually, when it is sitting on the surface, different parts of the surface is actually, different parts of the interface or the contact line are actually making contact with surfaces of different surface energies. So with that, how do we take this into account? This is a chemically heterogeneous surface. And finally, you can have a surface where the droplet is sitting on a surface, but it is not entirely making contact with the surface. It is uh, also supported by tiny cushions of air pockets that you see. These air pockets also change the net energy of the system, and therefore this can manifest itself as different angles. Now notice that in all these three figures, I have not used the equilibrium angle as theta. Why? The angle that I'm using the word equilibrium because these are in equilibrium. These are droplets that are going nowhere, they're stationary. But the angle is not necessarily, the angle that we see is not necessarily the Young's angle, theta y, but it's a different angle. So I've called it as theta star. And what we want to do is, in the next lecture, is to come up with a relation between this theta star, the surface energies, and the roughness parameters. That's exactly what we're going to do in the next lecture. I'll see you around in the next lecture. Thank you.